Hi everyone, I'm Borres from the School of Industrial Engineering and Engineering Management of Mapua University, and on behalf of Marco Malabrigo, Lorene Oleana Makasu, and Esmon Adriel Ramos, I'll be presenting a research study entitled An Experimental Study on the Performance of a Newly Developed Pico Hydroelectric Device. As the demand for the energy rises, national governments and private companies counterbalance it with the needed supply, and they spend years of research solely for ways of electricity generation. These energy production ways generate both positive and negative impacts to the environment. The continuous use of non-renewable energy has clear implications for our health and well-being, both of which are intimately connected with the impacts of non-renewable resources on our environment. There are 10 types of energy. Each energy has its own functions and has role to do work. Energy has two types, renewable and non-renewable. Its different forms can come from air, water, heat, and a lot more. Mechanical, kinetic, potential, and electromagnetic energy, or radiant energy, are being used for renewable energy. Renewable, as the word states, it can be reused. This type greatly uses natural resources that provides less pollution such as light, wind, and water. Non-renewable have resources that once used it cannot be used again. Most of the resources are extracted from the ground, fossil fuels, gases, etc. These resources are more commonly or conventionally used for producing energy, and it provides a greater negative impact to the world once used up. According to the Department of Energy, electricity consumption in the Philippines grew up to 4% from 2016 to 2017, from a total of 90,797,891 megawatts consumption from 2016. It grew to 94,370,341 megawatts in 2017. In terms of Philippine peso, in 2016, the consumed energy amounts to 59,508,937,761.4 and grew to 61,850,321,491.4 in 2017. In line with these values, it is evident that there was an increase of 2,341,383,730 in a span of 1 year. ASEAN countries continuously develop different energy resources through the use of current demographics and framework to cope up with the rising demand in an affordable and sustainable energy source. The trend of energy today tends to lean more on promoting and using renewable energy sources. Its advantages mainly focus on lessening pollution and promoting sustainability. Energy source shortages also do not apply to renewable energy. Less pollution means more growth and sustainability, which can greatly affect us positively through health, business, and all other factors. Renewable energy largely depends on resource availability, which means if there are less resources, there are less energy. However, its initial investment and cost of maintenance are high, so new technologies and innovations are continuously pursued to find the best alternative to generate energy. For the past 15 years, the ASEAN countries represent one of the key players and consumers of the global energy system. Through the years, the association's energy demand grew as buildings and transportation uses the most amount of energy in most of the countries. ASEAN countries continuously develop different energy resources so through the use of current demographics and frameworks to cope up to the rising demand in affordable and sustainable energy source. The 2017 nation's top demand results to 13,789 megawatts compared to the year 2016. 2017's total peak demand was 5.17 megawatts, higher than the 13,272 megawatts of 2016, but all-out power supply, as far as introduced limit, developed by 6.1% from 21,425 megawatts in 2016 to 22,730 megawatts in 2017. New capacities, which resulted to a total of 835 megawatts, were added to the nation's supply based in 2017, which incorporate coal-fired 630, 630 megawatts, solar 127 megawatts, oil-based 77 megawatts, and hydropower 1 megawatt. As far as offered by network, Luzon contributed 392 megawatts or 47%, Mindanao at 337 megawatts or 40%, and Visayas at 106 megawatts or 3%. Luzon supplied 392 megawatts, Visayas at 106 megawatts, and Mindanao at 337 megawatts, which is designated off share by grid. The year likewise observed the end of the regulated demand in Mindanao, which developed by 6.5% or 107 megawatts from 1,653 megawatts in 2016 to 1,760 megawatts in 2017, having only 1 megawatt on hydropower in the Philippines. It is evident that the government does not prioritize this industry. Indeed, Philippines is surrounded by huge amount of body water, with lots of commercial and residential establishment in different provinces can benefit from these resources. The following table shows the most commonly used appliances in every household level, whether it is from the rural or urban area. Based from 2011 Household Energy Consumption Survey in the Philippines, it showed that the most common energy source used by households is electricity. About 87% of 21 million households use electricity from March to August 2011. Other energy sources included in the survey are fuel wood, charcoal, liquefied petroleum gas, and kerosene. One third of the total number of households use these types of fuel. Water and energy correlate to each other. Water sector needs energy to filter and clean our water resources through treatment, pumping, and desalination. On the other hand, energy uses water to maintain, clean, extract energy producing facilities. The use of water in generating energy aims to promote a renewable type of energy called hydroelectric power or hydropower. It is the energy processed by the mechanical power to electromagnetic power using water. So the most portable hydroelectric generators on the market are designed to generate electricity from a vertical downward fluid flow in a pipe or tube. These portable hydroelectric generators are meant to produce lower power than that which is needed for an entire household. Currently, hydroelectricity in the Philippines is still further developed, with an estimate of 25 hydropower plants in the country. The Department of Energy states that the country still lacks power plant to filter the water produced by typhoons yearly. Hydropower can also be placed in most of the country's regions, but due to its cost, cuts were made and compared to other cheaper and more common energy sources. In this experimental research, a product design or prototype is to be experimented for its reliability and credibility to produce hydroelectric power. This prototype is meant to be the downscaled type of the bigger hydroelectric generating technology present nowadays. Downscaled because it is targeted to the smaller market in the household level to be specific. The researchers tend to have an optimized design for a universal and portable hydroelectric generator that can serve rural and some urban residences in the Philippines, and it is called the Aqualight. There are several considerations for the initial design of Aqualight, and these are portability, durability, head measurement, water pressure and flow rate, turbine power and turbine speed, consistent power output, environmental impact, and relatively low cost. There are available large hydroelectric devices, which has a capacity of more than 1,000 megawatts, and for small hydroelectric generators, which has a capacity of 1 to 15 megawatts. For this research to be successful, the researchers need to check the design factors affecting the performance of both large and small scale hydroelectric generators. These are the following: flow duration curve. This is the choice of turbine type, size, and speed based on the net head and maximum water flow rate, which must be determined by the main source of water where the turbine should be installed. Hydroelectric generators are normally built as a run of the main source. The maximum water flow capacity of the turbine must be determined by means of the flow duration curve of the main water source. Flow rate measurement or water pressure rate is essential to have the right flow rate and water pressure of the main source since it serves as a force to make the turbine running. Head measurement is the total vertical elevation from the location where the water enters the intake to the location where the turbine will be placed. Power output of a hydroelectric generator is determined by the pressure of the water at the nozzle and the amount of water flowing out of the nozzle. The larger the nozzle, the greater the flow. Turbine power measures the maximum output of a turbine. The rate of the mechanical energy will be converted into electricity. This is always associated with the power output in watts and affected by the turbine speed. And turbine speed is the velocity of how much the turbine blades are spinning. This is measured in the revolutions per minute. Different speed rate may vary the power output of a turbine and the whole generating system. The following are some of the innovations of power generation that use hydropower for small-scale hydroelectric generators, and these are the LH10001 and the Aurora Power Spout 2. These two Australian-made commercially product generators can offer similar outputs at similar inlet head pressure. The LH10001 is the most expensive, costing $2,975 and providing 25 watts with an inlet flow depth of 2 feet. This translates to $119 per watt. The second option, the Aurora Power Spout, offers an automated debris management system and 100 watts of output with a 1 meter channel depth. The system costs $1,599 or around $16 per watt. Another example is the T-joint. The types of hydrogenerators which were considered were Kaplan turbine, a turbine, and the water wheel turbine. They all they all have very different designs, and as such, the cost of materials varies quite significantly. With the use of the newly developed device that can produce 1 to 90 watts of electricity supply, the researchers would like to identify components or combination of components that can optimize the performance of aqualight in terms of first, electricity generated, and second, the amount of light that can be produced by LED light bulbs. We have four hypotheses that we would like to test. First, in generating electricity, our null hypothesis is there are no significant differences among the combination of different components or parts in generating electricity, and our alternative hypothesis is that there are significant differences among the combination of different components or parts in generating electricity in watts. In measuring the amount of light on LED light bulbs in luminance, our null hypothesis is that there are no significant differences among the combination of different components or parts in the amount of light on LED light bulbs in luminance, and for our alternative hypothesis, there is a significant difference among the combination of different components or parts in the amount of light on LED light bulbs in luminance. In testing the relationship between factors, the null hypothesis is first, there are no significant relationships between or among the different components or parts in generating electricity in watts. And for alternative hypothesis, there is a significant relationship between among the different components or parts in generating electricity in watts. In finding the significant factors, the null hypothesis is if the factor I is significant in the increase or decrease of watts in illuminance generated, and the alternative hypothesis is that factor I is not significant in the increase or decrease of watts and illuminance generated. The primary goal of this study is to develop the newly invented hydroelectric device by scaling, optimizing its design, building an effective water system to generate the maximum output in watts. This research aims to meet three objectives. First, to analyze the performance of the aqualight meeting an acceptable or meeting the standard power output of a Pico hydroelectric generator. Second is to identify design considerations and significant factors affecting the performance in terms of power output in watts of the hydroelectric device. Third is to be able to recommend the best combination of pipes, fittings, and motors based on the different significant design factors to generate the highest power output in watts units. This research focuses on the new hydroelectric device that regulates power for some 12 volts and 5 volts household devices such as LED lights, portable charger, and mini fans. The current hydroelectric devices that are available now in the market have disadvantages that leads to water waste. With the help of this study, the researchers would improve the most common disadvantage of the current hydroelectric device. The proposed device would have a water pump that recycles the regulated water to the reservoir to eliminate water waste and would have a continuous flow of water generating throughout the whole device. This study focuses only on the overall performance of the device, which includes the effectiveness and functionality of parts and its performance in electricity generation. This experiment would have at least 30 trials for the initial testing and 1,080 trials for the main experimentation. The study aims to promote renewable energy, mainly hydroelectricity, which provides energy at a low cost in using water. The study's overall goal is to find the ideal measurements and materials for the product to produce its maximum output for everyone's benefit. The government can deploy the product in areas affected by natural calamities. It can also be used in government housing in rural and remote areas. It is also beneficial for the industry because the product can be used for the promotion of renewable energy in the country, offering a new alternative in energy generation. Small and large commercial establishments can use the Aqualite in lowering fixed costs. Lastly, for the household, this study specifically will provide renewable energy generation for the household level, eliminating the top three household appliances or device that consumes the most energy. This conceptual framework shows the overview of the actual representation of the output of this research. The goal is to determine the best fitting or combinations that will be used to provide the highest possible electricity supply. This study aims to provide and help the researchers to choose the best design for a hydroelectric device. For this study to be successful, the researchers have set and made a framework to follow. For the initial phase, we analyze the performance of the newly invented device that cuts down electrical costs using alternative energy sources. Aqualite is designed to have three 12-volt ports and two 5-volt ports. The three 12-volt ports are used to light up the LED bulb, to supply power to the cooling fan, and to supply power to the water pump. The two 5-volt ports are used for charging cellular phones. The initial total power of this prototype, regardless of the pipe fittings, is three 12-volt turbine running in 2.2 amperes, having a 26.4 watts output each, plus two 5-volt turbine running in 1 ampere, having 5 watts output each, having a total output of 89.2 watts. This study proposes the use of these LED bulbs. It is said in the previous paragraph the working input of an LED bulb is only 12.5 watts. Cooling fans are at the same rate and cellular phone chargers are in 2 to 6 watts working input, meaning the least value of power that the Aqualite should produce to make the study acceptable and valuable is 12.5 watts, having at least 5.68 volts. Having this minimum power raised, the researchers can say that the study was acceptable and valuable. It means that the objectives are possible to be obtained. The initial design of the prototype was formed based on the factors that were mentioned in literature, and from those factors, materials that are needed were identified. The factor concerning the pressure, 5 different types of motors were tested and only one worked. It was the 6 liter per minute motor. For the factor concerning the generation of electricity, 3 types of turbines were considered since there are only 2 types of turbines in the market. They were the 5 volts and 12 volts rated turbines. Here is the schematic diagram of the Aqualite, and these are the materials needed for the device. The researchers must conduct these following procedures to show that the device is working. First is testing the power output in watt units to generate a 12 volts DC light bulb, its working input and its luminance as output. Testing the power output in watt units to measure a portable cooling device or portable cooling fan. Lastly is to test the power output in watt units to measure the rate of a normal 5-volt cellular phone chargers, the amount of milliamperes or milliamp hour electric power over time delivered in a phone battery. On this slide, the procedures on how to perform the experiment was explained, starting off with the initial setup of the prototype. Then we test the 12 volts DC LED bulb, 12 volts cooling fan, and a cellular phone charger using the device and record different response variables output for our statistical analysis. In our phase 2, our target is to identify factors affecting generated power in watts. We will be using regression, correlation, and ANOVA for different statistical analysis. On the third phase, we would like to recommend the best combination of pipes, fittings, and motors. To test the null and alternative hypothesis, the given list shows the different prototype setups with the different combinations of the number of turbines, volts, and motors. For the prototype setups, the researchers made use of the counting concept of statistics by using the factors and instance of variables to get how many combinations are there to be tested. Factor number 1, which is the type of water, has 3 variables. Factor 2, which is the temperature, that has 3 variables. And factor 3, which is the number of motors, which has 2 variables. And the last factor, which is the number of turbines and has 2 variables. So by counting, 3 times 3 times 2 times 2 is equal to 36. Therefore, there are 36 combinations tested and recorded. The following diagrams and statements are different setups for the experimentation. This is the list of the different combination of setups for single motors, and this is and these are the different setups for double motors. On our initial setup, we mounted the device directly to the faucet to check if it will work. There were 30 trials and each and every run were tested and recorded. There were no significant differences between the generated output in watts and lumens. Therefore, the prototype is running stable and have a consistent output. Using 4 setups in different water buckets, we will be having 30 trials for each type of water and water temperature, having 10 minutes running time and 5 minutes rest time. We have a total of 270 trials. The measured output for this setup is the voltages of LED bulb, fan, charger port, and the lumens of the LED bulb. These are the different combinations of factors used by the experiment. The given table shows the relationship of each variable to one another. The closer the Pearson correlation value is to positive 1 or negative 1, the stronger the correlation is. A positive correlation means that as one variable increases, the other variable also increases. However, negative correlation coefficients means that as one variable increases, the other variable decreases. P-value less than 0.05 indicates a significant correlation between the variables. From the result of the Pearson correlation, the number of motors is strongly correlated to watts and luminance. Same with the pressure. It is directly proportional to luminance and watts. Suction pipe also has an intermediate effect with watts and luminance. For the ANOVA result, the different levels for the different factors have significant differences, particularly the temperature and type of water and the number of turbines and motors. This is a sample ANOVA result for the temperature of water using the watts as the response variable. Since the p-value is less than 0.05, it means that some levels of the temperature of water have significant differences in terms of watts. And this is the sample result for the two-key pairwise comparison for the type of water used. The p-value is also less than 0.05, so it means that different types of water have significant differences in the response variables in terms of watts. The graph is a sample ANOVA result for the number of turbines used. The p-value is less than 0.05, so it means that there is significant difference in the output in watts if you're using 3 turbines or 5 turbines. The graph is also sample and over result for the level of pressure. Use the p-values less than 0.05, so it means that there is a significant difference in the output in watts if you're using a pressure level of 130 and 260. This is the result for the Navot test for the different suctions pipe length. The p-value is greater than 0.05, so it means that there are no significant differences among the different suctions pipe length. Their outputs in watts are usually the same. This ANOVA result shows that the number of motor affects the output in watts since the p-value is less than 0.05. For this ANOVA result, the p-value is greater than 0.05, so it means that even if you use 3 or 5 turbines, it will not affect the output in terms of luminance since they don't have a significant difference. In here, the p-value is less than 0.05, so it means the number of motors actually affect the output of light bulb in luminance. For this ANOVA result, the p-value is less than 0.05, so it means that for some pairwise comparison on the different types of water, there will be a significant difference in their output in terms of luminance. For this ANOVA result, the p-value is less than 0.05, so it means that the luminance from the two pressure levels have significant differences. The higher the pressure, the better the luminance is. In the ANOVA result, the p-value is greater than 0.05, meaning the suction pipe length doesn't have significant differences in their luminance output. In this slide, the Tukis shows that there are significant differences in the output luminance among the pairwise comparisons of the different combinations of factors in the experiment. Same with the output in watts, the Tukey result shows the significant differences among the pairwise comparisons of different combinations of factors such as the experiment. The regression result shows the regression formula that determines the significant components that will make a significant change in the electrical output in watts. The electricity generated by the hydroelectric device can be affected by the significant factors with p-values less than 0.05, like number of motors, number of turbines, length of suction pipes. However, the types of water, even if it's hot, cold, or warm, does not significantly affect the electricity generated. The researchers used decision analysis to create and identify the best possible combination of the device, weighted in 5 different criteria: cost, practicality, performance in lux, performance in watts, and reliability. The highest weighted score was chosen as the best combination. In doing the decision analysis, the researchers picked the 6 high-performing combinations based on output in watts and 11 lux out of the 36 combinations tested. These combinations were scored based on the 5 criteria with different weights. The criteria were formed based on the factors that we have considered in the earlier part of this research. Practicality was one of the criteria to emphasize the need for portability and the amount of effort the abuse would do. Performances both in lakhs and watts were also considered, basically because those are the response variables the researchers are trying to establish. Reliability was considered to check the performance of the device because it could be functional but not consistent, and cost is considered because it could make or break the product sales ability. Design 2 has the highest weighted scores, so therefore it is the design. The design has the combination double motor pump, 5 turbines, top water warm, having a model value of 49.6 watts and 314 lux as an output. It is essential to this study to know the value of the generated power, to know its Philippine peso value, and to know how much will be the user's saving in using the device. The researchers used the online electricity consumption calculator to get each appliance electricity consumption in hourly basis. This is to show the average consumption of an energy or most common problem in a household. Based from our estimated computation by using the hydroelectric device, the users can save up to 1,212.3 per month, or around 14,547.73 per year. For conclusion, 36 combinations with 30 trials each were conducted. Qualitative and quantitative analysis were done. 1080 values of watts output and 1080 values of lux output. It can be concluded there is a significant difference among the combination of different components or parts in producing electricity supply in watts and in lux. Water temperature, water type, the number of turbines, and the number of motors have significant difference in output both in watts and in lux. When temperature rises, water molecule becomes stagnant and helps the stability of the flow inside the pipes, giving it a higher output in terms of watts. Different types of water in the system has varying values. Increasing the number of turbines increase the number of output in watts but not lux. The number of motors coincides with the pressure of water because the system so the number of motors is directly proportional with watts and in lux. So therefore, this factor significantly affect the performance of the newly invented micro-hydroelectric device, Aqualite, and this result prompted further research of our system. Reduction of electricity costs for household and commercial establishment can be achieved by first using the newly invented Pico hydroelectric device with the estimated savings of 14,547,000 per year for a conservative use of LED bulbs, electric fan, and phone charging. Thank you.